Okay, let's talk about languages. So to remind you, a language is just a set of strings. Namely, we have an alphabet sigma, and L is a subset of sigma star. And we are interested, most of the course will be spent, at least the automata part of the course will be spent about discussing languages and their type and so on. So what are the standard operations we would be interested in doing on languages? Well, concatenation, taking two languages and A and B and looking on all the strings that we get from concatenating two strings from them. Union, of course, just the union of sets. Intersection, right? The language that is all the word that appears in both languages. In both, the strings in this intersection if it's present in both sets. And the difference, which is, all the words that appear in the language A but not appear in the language B. And finally, we have the complement operator, which here is a bit weird, which is just all the set of all the strings that are not in the language, right? Sigma star minus A. So this would be kind of our basic tool of the trade. And now we define L star, Ln, not L star, Ln as follows. Ln is just concatenating L with itself n times. So we define for n equals 0, we just define it to be the language containing a single string, which is the empty string. And for larger value of n, we define it recursively as concatenating L with itself n times. So if you want concatenating L with L to the n minus 1. Okay, and L star is, of course, going to be the union of all such concatenations. And L plus is going to be all the union of all L to the n, starting with n equal 1. Right, so we are avoiding the empty string, essentially. Okay. Okay, so we have a few questions. Let's answer them. So we have two languages that are part of binary string. So 0, 1 star just means all binary strings, right? So is epsilon equal to the set containing epsilon? Of course not, right? One is a string, one is a set. They are not the same creatures. No. Is the empty set equal to the set containing epsilon? Of course not. Here's a more interesting question. What is the concatenation of 0 and A? Well, it's going to be right, all the strings, right, x, let's just explicitly write it, right? It's xy such that x is in the empty set and y is in A, right? Now, of course, there are no string in the empty set, so this condition here is never going to be fulfilled. So this is an empty set. Okay, so empty set. Okay, and of course the same is true for this. This doesn't matter because the same argument implied that concatenating A with an empty set is the empty set. Okay, here's a more fun question. Maybe I should use a different color. So this is equal to the empty set we said. The set of sigma concatenated with A, right? So we take all the string in A and we concatenate the string epsilon to them, right? So this is going to just be A, right? Again, you can do it more explicitly. It's xy, right? In our case, in the first string have only epsilon, so x is always equal to epsilon, and y is in A, which means that xy is just going to be y epsilon, y in A, which is of course just A. Okay, so this is just A. Okay, and of course the same argumentation applies to the symmetry question. Okay, here's a trick question, right? What happened if A is equal to 2 and B is equal to 3, right? So how many concatenated strings can you have, right? So the naive answer is, of course, 2 times 3, but that's not true. This is, in fact, true only for if we take the Cartesian product, A times B, right? We are not taking the Cartesian product here. We are taking the 2 strings and we are taking their, product. We are taking the string and we concatenate them. In particular, it's not hard to show that this can be quite different than what you expect. So take A, for example, to be epsilon and 0, and B to be, epsilon 0, 0, 0, right? And if you think about it, the concatenation of A and B is just going to be A concatenated B. It's just going to be, sorry about the mess, should have prepared it in more space for this, but epsilon 0, 0, 0, and 0, 0, 0, right? So this example have 4 strings, and it's easy to see that you can get other values. So A concatenated with B is a set of strings that can be, it can have a range of values, as we saw, right, all the way from, 6 down to 4, and there might be an example even with 3. I would have to think about it. Yeah. Okay, so that was this question. Oops. Okay, more questions. What about the empty set to the power 0? Well, we defined any language, even if it's an empty language, we define it that if it's raised to the power 2, it's just the language containing the empty string. So that was by definition. Okay, if L is equal to, what is L to the 4? Again, it can be several things, right, depending on the words in the language and so on. In particular, think about the case where it's epsilon, L is epsilon and 0, then L to the 4 is, it's going to just be 0, epsilon 0, 0, 0, 0, 0, 0, and 4 zeros. And that's the possibilities, right? So in this case, we got 5, but if L is something different, right? For example, L is 0, 1. Okay, but let's take it more interesting. 0, 0 and 1, 1. Okay, just that, right? So it's a set of size 2, but L to the 4, clearly this is going to be 8 strings. Right? And to see why I got it, just write it down. Okay, so that answers this question. Yalla. Okay, let's do the other ones. Okay, let's do empty set star. Again, is essentially going to be the language with the epsilon as the only string. Same goes to epsilon star, right? It's also going to be just epsilon. Just go to the definition. Epsilon star, well, it's not well defined in our setting currently. What is epsilon star? It's a string, and we didn't yet define a star operational string. We will define it later on. So, right. So in reality, that's, in reality, without being too holy, this is going to be the set containing only the empty string. But why this epsilon star expression makes any sense, we will have to wait and see. Okay, when we speak about regular expressions. Okay. This is a cute problem. What is L if L star is finite? So the key observation is that if L contains any string, even just a string with single letter, then L star would be infinite, right? If L has one string which is not the empty string, then L star would be infinite. So this means that L cannot contain any string that have characters in. So L can be either two options. Either can be the language that contains the empty string, or alternatively it can just be the empty language, right? No words in the language. And notice that the two languages are distinct, right? One language has no string in it, the other one has one string, which is the empty string. Okay. Right. Okay, let's do maybe the final question, which is, what is empty set plus, right? So here, right, this is just going to be the empty set, right? To distinguish it from the star case, and epsilon plus is also going to be just, not also, it's going to be just epsilon, the language contains epsilon, and epsilon plus, again, it's not clear if it's well defined. Well, it's not currently defined in our language, but it's going to be just the language that contains the empty string. So that's the answer to all the questions here, and we can move on. Okay, why do we care about languages as far as computation, right? This course is about computation, not about sets and string and all this nonsense. So we must care about it for some reason. So the way to think about it is that deciding if an element is in the set is in fact computationally interesting, right? So for example, think about the set of all prime number. Set, let's call it P, which isn't a bad choice for later on in the course, but we don't care here. Set of all prime numbers. And what I mean set of all prime numbers, think about this set as, every prime number, I write it down as a string by writing it as in base 10 or base 2, it doesn't really matter. And now given a number, right, if I want to decide whether it's prime or not, I can ask, is this string in P? Does it belong to the language P? If it belongs to the language P, then it's prime, and vice versa, right? Another way of saying it, think about an algorithm that gets an input and have to answer yes or no, right? It's a yes-no algorithm. So this kind of algorithm immediately defines a language, right? Because you can ask what are all the input for which the answer is yes, right? And this is quite interesting, right? Because we can ask very difficult questions using this model, right? I can give you a program, right? What is a C program? It's essentially a string, right? It's just, we save it we save it on the computer as a file. A file is just a string of bytes, so it's just a string, right? So a computer program is a string. An input is, of course, also a file. It's also a string. So, and then I can ask, if I run this program on this input, would it crash or would it stop, right? So that's a very interesting question. Or is this, or we can ask more general questions which are not in this model, like, is the output of the program for this input correct and so on. But I just ask whether the program stops or not on this input, right? A pretty simple question, look pretty innocent, but in fact it turns out that we cannot write a program that answers these questions, right? So somehow inherently there are languages that are very simple, right? There are decision problems that computer can very easily answer them. And not only they can answer them, they can do it with very simple computers, which is inherently what we are studying in the first third of this class. And on the other hand, there are languages that are so complicated that no computer can tell us whether the string belongs in the language or not. And in some sense, we would like to know where the language belongs, right? So, usually when we speak about programming and programs, we care about problems for which we can not only, we can write a program that answers them. This program, runs efficiently, runs in polynomial time or in linear time or whatever we can do. So we care about efficiency, right? So at some level, the first third of this class asks, what are the languages that very simple computer can recognize? And when do you need more complicated and advanced computation model or computer to be able to recognize languages? Okay, and of course, this mapping between problems, or if you want, the yes/no questions and languages is bidirectional, right? Because given a problem, I can immediately define a language which is all string for which the answer is yes for the problem. And given a language, a set of string, I can define the problem which is, given a string, is it in the language or not? So speaking about languages is really speaking about decision problems. Given an input, does it have a certain property or not? So that's why we care about languages. Okay. And in fact, if you think about it, all the natural problems you can think of that are decision problems can be reduced to languages, right? You can reduce, for example, think about a philosophical question: is there a God, right? So we can define the language which is yes if there is a God, and we can define the language that doesn't contain only the string no if there is no God, right? So we have two languages, and one of them, is the correct set, of course. So those two sets are very simple, right? The answers are either yes or no, if you want to think about the God question. But of course, we don't know which set is relevant, right? So in some sense, this is not going to be a question that the computer can answer. Although, there are several science fiction stories that claim to have solved this problem. There's a very nice old story of Arthur C. Clarke called The 9 Billion Names of God, which is pretty good if you're interested. Okay, let's move on. Okay, so in particular, you can also think about languages as computing a function. The function gets a string and it outputs either 0 or 1. Right, essentially it's yes or no. For this input, the answer is yes. For this input, the answer is no. And this immediately defines a language because you can just take all the string for which the answer is yes. So computing such a Boolean function is immediately equivalent to a language, and then the computational question is, computing the function is equivalent to deciding if the string is in the language. Okay. So this is formally known as the language recognition problem. If I give you a language over some alphabet, the recognition problem of the language is to decide, given a string, whether or not it's in the language. And this is, as we said, equivalent to computing the associated function that tells us whether an element it's 1 if it's in the set and 0 otherwise. And as I mentioned earlier, our interest is in deciding and figuring out for specific functions, specific Boolean functions, how difficult they are. And I already told you that there are ridiculously hard functions. Of course, there are a very easy function, right? For example, is the string of even length, right? It's very easy to decide. You just go over the string and you count the number of characters in it, and you check whether it's even or odd. Okay. So how many languages are there, right? So And this is in fact turns out to be a completely non-trivial question, because what are languages, right? A language is a subset of sigma star, right? Sigma star is countable, right? But every subset of sigma star is a language, right? So we are looking on this power set of sigma star, and the power set of the power set of a countable set is not countable. This is Cantor theorem. So let's go through it a bit more carefully, maybe. So to remind you, a set is countable if there is a bijection between f, between the set and the natural numbers. And we already showed that sigma star is countable. And the set of all languages is the power set of sigma star. Officially, sometimes it's written also as power of 2, right? Because this is formally this is the set of all function mapping every. Okay, this is the set of all function from sigma star to 0, 1, right? Because you decide for every element in sigma star whether or not it's in the language, right? So officially, this is L, part of sigma star. Sorry, L is part of sigma star. Okay, and as I mentioned, the power of sigma star is not countable, right? In fact, right? So they are not infinite. Now, it's true. So this is not easy at all to see, because it is true that the power set of any finite set, if I have a set A, right, which is finite, its size is the cardinality of A. It's always for A, for A non-empty, the power set is always bigger, right? But this is for finite sets, right? Once you start hit infinity, it's not clear what is the size of this power set, right? So this Cantor theorem is in fact non-trivial, the fact that they are not equal, and in some sense, this is a theorem going back to, I think, the, late 19th century, and essentially it started set theory, right? And the rest is written in the history books, in the blood of students. Okay. And in fact, P of n, the power set of natural numbers, is in fact equivalent to the set of all real numbers. And we will get back to that. In fact, I hope that you had seen this stuff before. Okay, and there are many proofs. The basic proof of Cantor, and this is what the argument here in the slide show, the basic argument is a diagonalization argument, right? So here's what we are going to do. Think about creating an infinite matrix. 1, 2, 3, 4, right? The columns are going to be all the natural numbers, right? And now let's assume, for the sake of contradiction, that that the power set is in fact countable, right? So I can write down the first language, the second language, the third language, and so on, right? Every language is going to be a sequence of 0 and 1s. In the language, not in the language, in the language, and so on and so forth, right? 1, 0, 1, 0, 1, 1, 1, and so on and so forth, right? And the ingenious argument by Cantor was that let's take the diagonal, right? Let's take the diagonal, right? So the diagonal is just going to be this infinite string of zeros and 1, right? Let's call this language is well defined. Let's call this language S, right? So of course S, S is just a, it's just a language, right? So what do I mean by it's a language? for every, well, S is a set, right? We're not speaking about languages, we're speaking about sets, so if the confusion. So S is a set, right? Because if there is one written here, it means that the corresponding number is in the set. If it's 0, it's not, right? So S is a subset of the natural numbers, can you interpret it? And as such, it must appear in one of the rows of the matrix, okay? And that's okay, that's quite possible, and there is no contradiction yet. The ingenious part with Cantor proof is that he said, no, don't take set S, take its complement. Okay, so take S hat. S hat is where you take, this string of S and you flip the bits, right? And now it's easy to see that it cannot appear as a row in the matrix, right? Every set, we assume that P of n is countable. So every set of P of n must, because it's a countable set, must appear as a row in this matrix, right? Because we just count out those strings. So this not S must appear in the matrix, but then and let's assume it's the jth row, right? And then you look on the jth column, right, the number j, and you're asking, is j in this number? Well, if it's written 1 here in this matrix, then by definition, it means j should be in S, but then it's not in S hat, which means that this should be 0, and vice versa, right? So if you write 0 in this green entry, it has to be 1. If you write 1, it has to be 0. Both of the things are impossible, which mean that the set complement of S cannot be anywhere in this matrix, okay? And that was Cantor proof. Hopefully you'd seen it before. This was a bit hand-wavy. If you're interested, you should, maybe find a slightly more, a slow proof of that done more formally. It's of course available in the class notes and so on. Okay. So there are in fact deep consequences for computation because, as I mentioned before, programs are just strings, right? Programs are equal to strings, right? And the number of strings is countable, right? You can interpret a C file as just a really big number. So programs are countable, but on the other languages, right, if you want the problems that we are interested in, languages are uncountable, right, by counter theorem. So that's a contradiction, right? In the sense, it's a contradiction in the sense that there are going to be, if you want, this is the programs, right? And those are the languages, right? So the set of languages is tremendously bigger, infinitely more infinite, right? In fact, it's equivalent to the set Aleph, if you remember your set theory. It's equivalent to the set of all real numbers, the set of languages. So there are way more languages than any program can recognize, right? So inherently, there's going to be a lot of languages that no computer can recognize, right? Which is kind of surprising, but not too deep, right? This is, not too deep in the sense that this was known more than 120 years ago, right? The surprising part is that we can find such languages, right? There are explicit languages that exist. This is essentially Turing's famous contribution, right? The halting theorem of Turing. And his argument essentially goes to the same diagonalization argument that I handwaved in the previous slides. And this gives you an explicit, language that we can describe and is not in a set, right? And in mathematics, you have this situation where you have a set, you have another set which contains it, which is, infinitely bigger, and we cannot even find one element that's in this bigger set. Although we know that almost anything should be in this bigger set, we cannot explicitly easily construct them, right? So an interesting example of that is transcendental numbers, right? We know very few transcendental numbers. Although we know that most of the real numbers, in some sense, are transcendental. So, okay, back to our business. Okay, and this of course gives rise to a lot of questions. The first question is, we speak about programs, so what programming language, right? Should we speak about a C program or assembly programs or Pascal or COBOL, COBOL programmers still make quite a bit of money. In fact, they're making more and more money as time passes. So the question is what programming language we should do. So in fact, the church-Turing hypothesis says that it doesn't matter. All reasonable programming languages, or if you want, all reasonable computers are equivalent. At least in theory land. And as I said before, we want to know what are efficiently computable and so on. And part of this course is that we're going to try and come up with, or we're going to present, in some sense, the simplest model of a computer that is equivalent to a modern computer. Right? This is the Turing machines. And the amazing thing about Turing machines is that Turing defined them in the 30s, well before there were real computers. Right? So it was quite an achievement. Okay. So let's start to speak about easy languages. If a language is finite, then it's easy, right? Computationally, it's of course easy, right? You just list all the string in the language, and given an input, you can just check whether the input string is one of those strings. Okay. So another interesting claim is that the set of finite languages is countable. So let me give you a hint how to prove it. Just think about how to write such a set and define the language which is, have a string for every such language. And then this language would be would be contained in some sigma star for the right sigma, and it would be countable. Okay. And that's it for now.